out that if instead of that you do the regular Fourier transform, and then you do some phase shift of the coefficient, you're extracting the same coefficient that you would get if you would do the Fourier transform.
Because it's just like, so it's like you're multiplying this whole thing by doing computations. Okay, so that's because normally when you think about changing the weights, it's not about phase shifting. It's just changing the level. Okay.
זה נובע מתוך
מה היה שפשע? אולי שפשע זה יותר נבוא?
כולם נאבד
יש את הוקטור K, יש את הוקטור שעושים ממשי, יש אחד משמעות של השם.
ואני חושבת שבצורת האלה ולא קטנים
אבל בעצם אחד מהמשמעות של השם, יש שמן כבר של
לא זוכר מה יש לנו,
אנחנו חלק
אנחנו כבר חישבנו,
זה מה שעלה אקטיבי. אם היינו במקום טרנספורם פורייר מורכב, עושים טרנספורם של קוסמוס, החלק הממשי והחלק המדומה.
אבל מה זה בסעיף 4? אם היינו מבינים כן,
זהו, זה גם משהו שלא מבינים.
כן,
כי אם באמת זה לעשות נפש.
כמו דבר מקרים לעשות המודל של ה-W הזה. שהוא במרחב הממשי.
היא חברה של תשת הפסקריה?
בואו צריך להיות מסתורים אנשים.
כאילו בעצם נגלה זה יוצא
לא, יש עליו אילוץ. המספר של השור,
כן, זה מספר של השור.
לא חיובי רעיון. המספר של שמונה כל
היו ילדים
שיפוע לחד שלו.
יותר תמיד מתחברים. לא, תעמדו לאחרון ברק שזה
זה לא ממש לא עכשיו.
יכול להיבחר כך. טוב. אוקיי.
Oh, I forgot to bring my laptop. Cute.
זה גדול. חילופי ידיים זה יכול להבין. אתה הבנה משתתפים כאילו פיוט ויחסים מה אפשר להגיד? מה יש לי להבעיה פגילה? מה השתנה בסתורי?
לא, זה לא שנה.
אז למה הוא עושה כלום? יש לי משהו שאולי זה רק אני, אבל מה זה שונה מהבעיה הקודמת שלנו עם ה-WPC שחישבנו והכל?
כן, אני אענה על השאלה לכולם, אבל...
אוקיי, נתחיל.
למה חסר לך שזה?
מספר בינוס.
מה? כאילו,
Okay, so I was asked to explain how is what we're doing now different from the general discussion that we did when we discussed the WPC solution. Now it's not different. We're using what we've done for the WPC solution. But remember, in the WPC solution, what we were doing is that we could interpret the matrix W as doing first two things. First, a transformation that extracts the coefficients of the principal components, and then encoding each one of these coefficients independently. So it's that matrix times its diagonal matrix. we know that this is not how the reflective fields in the retina look like. I mean, if that would be the case, the reflective field, each retinal ganglion cell would encode a particular Fourier coefficient of the input, meaning that its reflective field would be sinusoidal, spread around on the whole visual scene. That's completely unrelated to what the retinal ganglion cells are doing. But now we remember that there's also the freedom to multiply by a unitary matrix. And what we saw now is that, and this was somewhere over here, is that if we assume that our W is circulant, which does match reality, because we know that different receptive fields have the same structure up to translation. If we assume that, we see that we can write W transpose in this way. And now how do we interpret it? This part is a unitary matrix, fine, we're allowed to use a unitary matrix. This part does exactly what the WPC solution does, because it extracts the Fourier coefficients and then multiplies each one. This is a diagonal matrix. So it extracts the Fourier coefficients and then multiplies each one of them by a constant. So if we wouldn't have this in front of it, this would be a matrix W that represents really the WPC solution. It would be an encoding of each one of the Fourier coefficients independently of the others with some free factor. But our theorem told us that that's the best thing that you can do up to a unitary transformation. We have the unitary transformation here. So this has to be the WPC solution. Okay? And now everything that we've done, the whole work that we've done on WPC solution, I kind of glanced through it, but it's crucial for finding the solution, because we need to have it written down previously. We need to find the square root of alpha I. These are given by the equations that we derived for the WPC solution. Okay?
So the ganglion cells still do the optimal solution, just to multiply by some of the...
Yes, exactly. So this is our hypothesis. Or this is what the theory predicts that they should do. Okay?
And they do do it.
Well, okay. Now the question is, does this theory predict well the structure of receptive fields of ganglion cells? We'll discuss that in a moment.
Did we start with that? We said that the receptive field is not just...
Well, the question is whether the detailed structure of the receptive field is predicted by the theory. It's not just the fact that it has translational symmetry, right? And how does the structure of the receptive field depend on parameters? So we know that there's one thing that we can easily vary, and this is the input noise. We discussed this in the beginning, because as we change from high luminosity to low luminosity, we're essentially changing the input noise. So the question is, does the theory not only predict for one value of input noise what will be the structure of the receptive field, but does it also predict how the structure of the receptive field should change as we go from one value of input noise to another? Another thing that the theory tells us, which I'll discuss in a moment, is something about psychophysics. It tells us if we know what is the factor that our visual system is applying to each one of the frequency components of the inputs, we could predict what would be the minimal value of value of stimulus at that frequency that we will be able to discern. What does it mean that we will be able to discern it? The amplitude should be large compared to the noise. So the theory allows us to predict something about the minimal magnitude, say, of a grating with a certain frequency, which is superimposed on a uniform background, that we will be able to identify. And I started my discussion on this topic by showing you experiments from the 50s, 60s, which measured in great detail what is the performance of different subjects at different, showing gratings at different frequencies, at different background luminosities.
That's not ganglion cells, that's the whole brain, no?
That's right. That's a very interesting point. So this is the whole brain. Now the question is where is the limiting factor? Is the limiting factor in our retina or somewhere else? But it turns out that the theory, as I will go back to this plot and show you, the theory predicts very well the whole set of psychophysical curves for different values with only 3 parameters. What are the parameters? The parameters are the input noise, the output noise, and the constraint. Okay? So this gives a set. It doesn't prove it, but it suggests that indeed the limitations are psychophysics. The limitations of our visual system in this respect come from the retina. And it's really not it's I think it's not even correct to say the retina. The essential limitation comes from the optic nerve. The reason why there's some limited amount of information that can be sent from the retina to the brain, that all this has to go to the optic nerve. So it suggests that this is the real limitation of the system, and beyond that, our brain can interpret the information sent from the retina more or less optimally. Okay, so, but
Evolution can change the amount of neurons in the retina and the amount of fibers then.
right, but maybe still, I mean, it would be, I mean, there's a huge number of fibers going through, it has to cut through part of our visual scene. We have an area where we don't see anything because of the optic nerve. So
Okay, but there is another limitation that you need to do.
Of course.
The amount of neurons and why we have X neurons, not Y neurons.
right, that's absolutely true. So what I want to show you now is just some calculations. I mean, you will do an exercise where you will go through this calculation in a one-dimensional model and calculate receptive fields for different values of input noise. And I will show you an equivalent calculation that I did in 2 dimensions. Just to give you an idea that it really does something that makes sense. Okay, good. Okay, here's my code. It's very interesting. But you see a parameter epsilon, which is really the input noise. So this is what I'm going to change here. I have, let's see what else I have here. I'm assuming that there are, what?
The variance of the input?
The variance of the input noise, yeah. I mean, it's what we call epsilon in the equations, and there's also a delta, which is the output noise. Here's eta, which is what I assume for the... Now, I'm assuming that it's a 1,000 by 1,000 input, and so the photoreceptor array is 1,000 by 1,000. And P, for the two-dimensional case, is in each direction. So there's a convergence from of factor 10 in each direction, meaning that ratio from photoreceptors to ganglion cells is 100, which is about right. It's about right, by the way, it's about right in the periphery of our visual scene. It's not true in our fovea. So everything I told you about convergence in the retina is true everywhere except the most important part of our vision. In the fovea, our system, I mean, presumably the fovea has developed to provide as much as the best possible resolution. So in the fovea, there's a one-to-one correspondence between photoreceptors and retinal ganglion cells. And in fact, what is the structure of retinal ganglion receptive fields in the center of the fovea is not known very well. There's very few, I mean, people always record a few degrees from the fovea. But, okay, so this, we should imagine that this is peripheral vision. And, okay, I will just run this. Is anything happening? Okay, I will skip these plots which have something to do with the psychophysics, predictions for psychophysics. I will not discuss this now, but what's going on? Sorry. This is very good. Okay, you don't even see what I'm talking about. Okay, so this is what this is what I was talking about. I'll erase this, and now here's the receptive field that I got. So I did all that has to be done. I mean, you have to find what do you have to do? You have to find you have epsilon, you have alpha, you have the lambda. So you have equations for the alpha I. Equations for the alpha I still depends on the constraint, so the Lagrange multiplier. So you have to search for the value of the, so for each given value of the Lagrange multiplier, you can calculate what will be the total variance of all the outputs. And then you need to search for the value of the Lagrange multiplier for which you obey the constraint. And then for that value of the Lagrange multiplier, you have your final alpha I. These become as I discussed in the one-dimensional case, the WIs, and then you inverse Fourier transform to get the receptive field. So here's the receptive field that I got in this case. I'll try to turn it around a bit. It's kind of a surround receptive field. I wouldn't pay too much attention to the ring that you see here because it's already comparable to the size of our whole array. So in principle, we would have wanted to have a much larger array even because the retina is not 1,000 by 1,000, it's larger. But more or less, this is the center of center.
What's the exact detail?
Okay.
The 400.
So this is just the horizontal axis is a retina, right? So this is a imaginary retina with periodic boundary conditions in this direction and in this direction. It's like a torus. And this is a prediction for the receptive. Now, so the y-axis is the W, right? The height. So our retinal ganglion cell, which is here, which is at the center, our prediction is that it will sum up the input from the photoreceptors with this function. All right. Now, what I'm going to change is the.
For specific ganglion cells?
Yeah, but all the other ones are just translated versions. That's all there is to it. In this case, they will be translated because I have convergence, they will not be translated by 1, but they will be translated by 10, by factors of 10. I should have maybe discussed this, I mean, I didn't yet discuss with you what happens when P is finite. I'll do that after this demo. So now what I want to do, if I just manage to control my mouse, is to switch to a low input noise. So I'm just switching epsilon was 10 and I'm switching to 0.001. I'll run it again. And so what you can see is that several things have happened. First of all, the receptive field became narrower. And it kind of makes sense that actually when there's lots of noise, we want to average over a large area in order to overcome the noise. But when there's little noise, we might want to average over a low area. But the other interesting thing which is happening, which is when I rotate it, we will see, is that there's a surround. Okay? Now again, I wouldn't pay too much attention to the wiggles that you see afterwards, but there's a very clear surround. So this is really a center surround receptive field.
So why only with low input noise? Why does it show only with low input noise?
Okay, so this has to do with the reasoning that we discussed previously, that for low input noise you enhance the high frequencies. And so this means also that the receptive field has high frequency components in it. The function of the receptive field has high frequency components, so it's oscillatory. It's not very oscillatory, it has at least this goes from positive to negative. And for low input noise, but this is also the other interpretation that we gave to it, is that in this case you're actually calculating something like a derivative. You're asking what is the difference between this pixel and its surrounding, which is more informative. You're removing in this way the correlations that exist in the visual scene. In the visual scene, nearby pixels are correlated. If you take differences, you remove this ambiguity, redundancy. Okay, so the last thing that I want to just show you is one point about the phases. I mentioned to you that there's this freedom to choose phases randomly, any phases for each one of the outputs, but the choice that gives the narrowest receptive field will be the one where all the phases are real. And just to demonstrate that, I'll take the same case and just, I have in my code a line that if this is 1, it just multiplies each one of the phases by a random phase. Okay, it just chooses a random phase for each one, and the complex conjugate random phases for k and complex conjugate for minus k. Just let's see what we get for the receptive field when we do that. Okay, so you see that it's much more extended spatially. Okay? And so indeed, when you choose the phases to be the same, you get the most localized receptive field. Okay, what I still didn't do is discuss a bit what happens when, from the point of view of the theory, what happens when P is finite. But actually, there's something that I want to do before that. I want to remind you of things that I showed you. So one thing that the theory predicts is the structure of receptive fields. But the other, as I mentioned, the other thing that it predicts is just the psychophysics, the sensitivity to different frequency components. And I remind you that I showed you this plot when we started. This is from 67, Van Ness and Bowman. And what they measured is they had a uniform illumination with some intensity I, what is called the I bar. And then on top of it, they overlaid a grating with some frequency, varying frequencies. These are different frequencies. And they checked what is the minimal amplitude that human subjects were able to identify. Okay? And then these different curves are at different background luminance. And we discussed the fact that larger luminance means that there's more, the background luminance means that our eyes are bombarded by photons, and this is random. So there's a variance or noise which is proportional in variance to the luminance. The standard deviation goes like the square root of the luminance. Our visual systems divide by the background luminance just to normalize for different light intensities. So essentially, when there's low luminance, as I'll show you in a moment, it's as if we have high noise. Low luminance is like high noise. And as you go from low luminance to high luminance, you see that there are several things that happen. One of them, so what is shown here, this is a spatial frequency, and this is the minimal observable amplitude of the grating relative to the background. Okay. So if there was no noise, no noise at the input, we would expect that this would not be dependent on the luminance. But what you see here is that as you increase the luminance, we're able to discern smaller values of, this is M, okay? We're able to discern smaller values of M. And when we're at low luminance, which is high noise, the frequencies that we're most sensitive to are the low frequencies. So this matches the prediction that at high noise, high input noise, we devote the most of our resources to the low frequency components, which are the ones with the high variance, right? The low frequency components are the ones with high variance. Remember, it's 1 over lambda to 1 over k to some power. But once we enter a situation where we have higher luminance, something dramatic changes. Now our visual system becomes more sensitive to some finite frequency. And this has to do with the structure of the alphas that the theory predicts. The theory predicts that once we have enough, when the input is sufficiently low, the noise is sufficiently low, then the alphas are non-monotonic functions of k. We devote more resources to finite values of k than to small values of k. Okay, so this is what starts to happen here, and we are able to, the frequency of the grating that we discern the best becomes higher. And if we continue to decrease the input noise by increasing the background luminance more and more, to some stage, our visual system doesn't improve anymore. This curve and this curve are almost the same, although there's still a factor of 10 in the luminance. And this just tells us that our visual system cannot encode anymore. Cannot do any better because of the limitations of the optic nerve. Now, what I want to show you here, I showed you this to you previously. This is really the same plots, just turned around, because what was called the sensitivity M is now something more like 1 over M, which is called new constant sensitivity. But each one of these curves corresponds to one of the curves that you saw previously. Again, this is spatial frequency, and the symbols are the same for the data from the experiment. But the curves are predicted by the theory of efficient coding with 3 parameters. The 3 parameters are the magnitude of the input noise, the magnitude of the output noise, and the constraint. Okay. So the fact that you can predict not just one of these curves, but the whole way that the structure of these curves changes as a function of input noise, I think is really very suggestive that this theory captures something real about what the retina is doing.
Which constraint was used here?
Well, it fits. It's some constraint of the total variance. You have to fit it so that you will.
But I'm saying, was it like a mean squared or what?
Yeah. That's a good point. So if you would look at these papers, so this is Attic and Redlich. I put them on the Moodle. These papers make a particular prediction, as you asked, about the constraint sum over the variances, and it's not obvious that this should be the correct constraint. And in fact, if you would use some other form for a constraint, you will get somewhat different predictions, and we'll not discuss this more. But indeed, there are some questions about this theory. It is obvious that this is a correct theory, but still it's doing a very good job. So what I just want to mention briefly, still on the whiteboard, is 2 things. So maybe first I'll continue with this and just mention what does it mean to calculate the sensitivity for different gratings. I mean, how can we get from the theory that we developed here? How can we predict these kind of lines? So I will just do it I will just do it kind of qualitatively. Okay, so imagine that we have some input luminance I bar. Okay, this is the background. And on top of it, we overlay some grating with some amplitude, delta I. Delta I, cosinus k. So this would be our stimulus. And we really want to understand at what delta I you can start to see that there's a grating overlaid on the background. Now, we imagine that most of the light coming to our retina is coming from the background, not from this. So the input noise is dominated by the background. And therefore the variance of the input noise is proportional to I bar. If you have, 1,000 photons falling on your retina, per unit area of your retina per unit time, then the variance over that time will also be 1,000. So this is the input noise. Now, our visual system is normalizing by I bar. So after normalization, after dividing by this, we'll have here 1, and here we will have delta I over I bar cosinus kx. And this is what we called M. The value of this quantity is what was measured by Van Eff, right? So we want to ask at what value of M we would be able to identify the grating. But now, when we ask what is the magnitude of the noise after this normalization, so now the input noise after the normalization so our stimulus is this divided by I. I claim that the input noise is going to go like 1 over I. Why? Because we divide we have something which has variance I bar. We divide it by I bar. So standard deviation of this quantity is square root of I bar. Standard deviation of what is going on here is the square root of I bar divided by I bar. So the variance is 1 over I bar. So after the normalization, the variance of the input noise is 1 over I bar. So this is what we call epsilon in our theory. This is the input noise. And now I'm putting here a proportionality because there are some factors that are constant, but we didn't take into account. What is the size of the grating? because actually when we try to identify the grating, we need to average over the whole visual scene, so the size of the grating and various other factors. But the variance will be proportional to 1 over I bar. And in addition, in our theory, we might have some output noise, delta, and everything else. But essentially, for the grating, what happens to this grating by our visual system? Our visual system is taking the Fourier transform, essentially, doing the PC solution, and then inverse Fourier transform. But essentially, this frequency component, which has a variance m, which had the amplitude m, or maybe this is it's multiplied by the alpha. The variance is going to be multiplied by the alpha I. I think this should be really m squared because this is amplitude, but I'm not sure. But it doesn't. And then we have the input noise, and then we have delta. The variance. So the variance in frequency k is going to be this thing. And now the question is, what we're asking ourselves is, what is the value of m for which we will be able to identify the stimulus? What does it mean that we need to be able to identify the stimulus? It means that the signal should be larger compared to the noise. So identification means that alpha I n squared should be larger, so this will be the threshold. Alpha I times n squared should be larger than alpha I epsilon plus delta. So this gives us, now the alpha I themselves depend on delta and epsilon. And so for every choice of epsilon and delta, we can predict what are the alpha I's, and then what will be the m for which we will be able to identify the stimulus, in which where the signal will be larger to the noise. And this itself is a function of k. So I don't want to go into the details and do this, but just to point out that the theory in this way tells us what the psychophysical curve should look like. And this is what Attic and Redleff have done.
The theory is what they measure.
And I showed you. I mean, the theory with 3 parameters predicts very well the whole set of experiments of Valet. And in addition, just a second, and in addition, it predicts very nicely the structure of the receptive fields themselves. Okay? Okay, so this is so if you were wondering why any of this is related to the brain, it is really related. It's one of the most beautiful predictions, quantitative predictions, on something that the neural system does. Okay?
Yeah. So just delta I is some constant?
Delta I, where do we have delta I?
Or
Delta is just the output noise, which we assumed is a constant. Whether this was we assumed that in the output unit there was some noise.
I mean, up there at the top.
Okay, yeah, so it's not the same delta.
Yeah.
Yeah, delta I is just what the experimentalist is varying. The experimentalist is overlaying the background. The experimentalist is overlaying on the background the grating with some amplitude.
Okay, but the delta I or triangle I, that's just a constant, and then the variability comes in because of the cosine kx. That's the idea.
Not really. The variability. Okay, why I mean, this is the spatial structure of the stimulus. There's variability in what the brain receives because of noise. The noise is each one of the photoreceptors is activated by something like this plus noise, and the noise is actually the same for all the photoreceptors because we assume that the stronger illumination is this part. This part is just constant. And so there's a certain number of photons falling on each photoreceptor per unit time, but this is a random variable.
Yeah, so that's fine, but is delta I a function of x, or is it just...
No. Delta I is just a number. And the experimentalist is varying this number, and what they actually report on is delta I divided by I. This is what they call m. And they tell us at what value of m was the subject able to say that he or she was seeing the stimulus? Right?
And that answer varies depending on what...
Okay, so yeah, it will depend on k because the alpha i's depend on k. so at very low frequency, at very low input noise, the alpha i's are larger for larger k, and so it will be easier to discriminate the larger frequencies, which is what we saw. And for very high input noise, the alpha i's are decreasing as a function of k, and it will be easiest to identify grating with a low frequency. And all this matches beautifully the experiment. One last thing that I wanted to say briefly is what happens when there's so I discussed here the case of p equals 1 or m equals to n, and but I showed you in the demo that I showed you, first of all, it was two-dimensional, but also p was 10. So let's just think for a moment what would happen in the one-dimensional model if p is positive, larger than 1. Okay, so n is equal to p times m, p larger than 1. So the first thing that we know is that we have convergence. The number of outputs is smaller than the number of inputs, and therefore the theory predicts that the system should somehow throw away all the frequency components that are the larger ones, because it should take the ones with the highest frequency. And the structure of W, if we assume that receptive fields have translational symmetry, as we assume also in the case of p equals 1, then how does W look like? First of all, it's a n by m matrix, right? Sorry, this is W. W transpose is like W transpose multiplies the vector of size m and generates a vector of size m. So W is like this. Maybe I should draw it. I should draw W transpose just a bit more clear. So W transpose will be n by m matrix, right? And maybe this was also no. Sorry. Okay, fine. My confusion. Okay, it's n, right? I mean, if we multiply a vector of size n, fine. So this is n, and we get out a vector of size n. Okay, so again, we can interpret the entries here as the receptive field. But now, how will the receptive field of the next neuron look like? So previously, in p equals 1 retina, the next receptive field was shifted by 1. So how should the receptive field of the next neuron look like here? Shifted by p, right? We have, for each ganglion cell, we have p photoreceptors. So if we move to the next ganglion cell, it's like moving p photoreceptors to the right. So if I would put here WP, then W0 for the next line will be here. And then we'll have the next one here, and so on. Okay? So this is what we predict for the structure of the receptive fields. But this means that this is a structure of W. And so in order to formally understand what's going on, we need to understand some properties of matrices that look like this. So a matrix that looks like this, a circulant matrix, we know that it's diagonalized after you do a Fourier transform. A matrix that looks like this, which I will call a generalized circulant matrix, also has interesting properties, and later we'll go through them with you. And but what I will want to tell you after you do all the work is what the answer. How do you predict the receptive field? So the answer turns out to be very simple. It's very similar to the prescription that we had for the retina with p equals 1. So I will just write now, without proving, I will write the correct prescription to obtain, to find the effective field, W0, W1. So here's what you need to do. You first need to find the Fourier transform of this function. And how do you find it? You set Wi tilde to be square root alpha I for the first m frequencies, for the lowest m frequencies, and 0 for the rest. Okay? So remember, our theory tells us that we will have m square root of alpha I because we throw away the components in the inputs with large frequencies, we take the lowest m frequencies, and each one of them, if it was a WPC, this was a WPC solution, we would just multiply each one of them by square root of alpha I. We have a prediction for square root of alpha I. So now generate, imagine this, so the Fourier components of Wi are going to be in the lowest m frequencies, these numbers, and 0 in the other ones. And then you just do an inverse Fourier transform. Okay? So in the case of p equals 1, it's just, you know, this, it's like this, but without the one that you set to 0. That's the whole difference. Okay. Done. So on Thursday, I will talk a little bit about an interesting problem which is called independent component analysis. Maybe I'll just mention to you what it is. So imagine that you have a set of inputs, n inputs, but these inputs are actually some mixture of other sources which are statistically independent of each other. So for example, I might listen to, we might be sitting in a room and have several microphones, okay? And each one of these microphones is picking up sound coming from several sources with some amplitude. So each microphone is picking up all of the sources with amplitude that depends on the distance from them. And now all the sources are generating sound, but they are independent of each other. So the question is, can we take the output of the microphones and apply some linear transformation such that we will demix the inputs, and we will get the different inputs. And is there a principled way to find the amplitudes that would do this? Another example could be, so this is something that might be related to what our auditory system one might want to do. Another example might be in olfaction. We have a set of different receptors. We have different receptors. Each receptor is sensitive to various chemicals, but the chemicals, so each receptor is sensitive to many chemicals, but the concentration of each one of these chemicals might be fluctuating independently. We might have some different sources of odor that are fluctuating independently. Can we separate them? Now, why does this matter for the brain? It matters for the brain for two reasons. One, it might be computationally an important goal to separate sources of that are affecting our stimuli, our sensory organs. It is also important from the point of view of coding, because remember that one of the reasons we did PCA when we the reason that we did PCA when we did the transformation from n inputs to m outputs is that the principal components are statistically independent of each other. So by taking our stimulus and transforming it to components which are independent of each other, we're removing redundancy. We're not encoding the same quantity more than once. Okay? But we assumed so far that our inputs are Gaussian. And for Gaussian inputs, removing redundancy means taking the principal component. What we will see on Thursday is that for stimuli or sources of information which are not Gaussian, that's not necessarily what you want to do. And what you really want to do, if the model is that you have independent inputs with some statistics which is not Gaussian, there's something else that you want to do in order to mix them, and then you're encoding separate sources of information. So maybe I'll repeat this argumentation on Thursday, but this is what we will do.
פתאום עלו לי שאלות ובדקתי עוד פרקים ודברים כאלה.
זה טוב שאתה מעדיף, גם אם אתה עכשיו יש לך שליחים שאתה צריך לעבוד עליהם, עדיף שתגמור את הכל, תהיה רשום פה כשאתה מתחיל באמת את
הדדליין זה מי שנוגע חזרה.
פה בקרוב.
כמה שהבנתי בשבוע הקרוב.
אני גם עסוק בזמן האחרון כל הקיץ הייתי עסוק בכתיבה של מאמרים, ועכשיו זה חמות עם
בדרך כלל זה ראש כאילו הלא פינג פונג הזה?
כן, זה יהיה, סביר, זה נוח. שומעים נוח. יותר לעשות שכן.
תגיד לו שאלה, נכון שאמרנו שאפשר רק כדי פאזה משנה כאילו בתור לפי פאזה אחרת.
נכון.
כמו שהיא כאילו זה תוצאה
זה התפקיד שלנו. אני מאוד שונה ככה באמת. מה? אני אומר לו, מה זה כל פרופסט מתערבבת? אבל כן.
זהו חי.
אבל ידעתי חיים הוא לא ממלכתי, הוא כאילו רוצה לראות שהמדע בסדר, וזה זה נגמר. ולא זה מטילה כאילו, ככה זה כבר, זה כאילו ברור.
כן, זה כבר קוריאני.
קיצור, זהו, כאילו זה איפה היה שפתאום שפתאום סקירה, אני לא הסתכלתי את המאמר נשים כאילו אמרו לי להתחשב זה כאילו מה שעשיתי זה שהם קיבלו את זה הם כן הלכו, כאילו הם בעיקרון זה לא היה 60. אז כאילו, פשוט היה בסדר, אבל...
כן, מזה אני יכול לעשות. אבל בכל זאת אני מרגיש שאתה...
כן, זה מלא עבודה, נו.
Hi, my name is Itamar. I'm a fifth-year student. I'm here at Delta, working to find some work. In the administration has kindly hired me as a tutor for help for this course until the end of the semester. So you can be in touch with me. Things I've already told you, but I just wanted to come show my face. Who I am, you can write me an email and schedule a time. Depending on the number of people that are interested, it can be private discussions, private hour, or with groups. Until the end of the semester. So, yeah, you have a very caring administration. Take advantage of it.
No, I really like Itamar more than the best I could ask for this course. So use it if you need. I'm not sure that next year we'll have this kind of tutorial.
Whenever we want, we want to be here.
Okay, schedule time.
You,
Schedule time
yeah,
to meet. Sorry, set a time.
You're lucky.
As far as privately or with a group, it's up to you. So I'll have to just figure out as far as how many hours. Schedule me for 4 hours a week total for the class. So if there's only one person that wants it, so you can have me for 4 hours this week.
But especially for people that need help and physics and mathematics is too hard, like don't wait till the end of the semester because
Okay, I'll write my email here. Small.
I already sent it to your session, so you have it in the Moodle, but
Okay. Good to meet you. I might go get some food and come back just to hear that. That's for fun.
yeah. So before starting, in the last exercise, too many of you did the following mistake, which last week were very angry, okay? So this is not, okay, equal to this, okay? And we're angry because, no, the problem is that too many people did it, which means that you are probably copying the answers of each other without even looking what you are writing, okay? So, no. Okay, don't do it again. Okay. So today we're going to talk about dimensionality reduction in the retina. So Yoram have already talked with you about dimensionality reduction from one hand and from the other side about the properties of the receptive field in the retina. So today we will combine these two issues. Okay, so we're still in the okay, so we're still in the general framework. We have x from Rn that goes to y, which is n-dimensional, okay? And only today, only in this specific context, we will assume that n is equal to Pm, okay? Where P is an integer. Okay, so today for simplicity, we will assume that these are not just two numbers, but also m is an integer number of m, okay, the lower dimension. So the general PC solution, so I'm not going to write again all the assumptions of the model, the Gaussianity, the exact set, because you have it in your notebook, okay, but if you feel that something is missing, so ask me. So we've seen in class that what is WPC solution, what is the general form of the WPC solution?
Of alpha
Yeah, so we have the diagonal matrix of the alpha, right?
multiplied by U transpose.
Yes, and here we have the eigenvectors of what?
Covariance matrix.
Of the covariance matrix thing, okay? So in case of the retina, maybe I will write this part again. So what are the eigenvectors of the covariance matrix in the retina? What we assumed about the statistics of the input to the retina?
And it's translation invariant, so
That's
it's
okay.
Fourier components.
Okay, so we assumed in class that x transpose is a circular matrix. Okay, and that these vectors are the eigenvectors of the circular matrix, which are the Fourier vectors. Okay, all of you know it already, hopefully. Okay. Okay, so here, we choose the n Fourier vectors with the largest eigenvalues. Okay, so the largest eigenvalues are determined by the statistics of the natural images. Okay, so we assume, so also in class, Yoram told you that the principal components are the Fourier vector with which kind of frequencies? Can you remember? High, low, low. Okay, so the principal components are the Fourier vectors with the lower frequency. Okay, so this will be the m Fourier vector distribution. So, and in this case, so when we say low frequencies, these are low frequencies in the absolute value. Okay, so actually we see the frequencies of k between Okay, so these are the low frequencies that we are taking. So instead of writing the WPC in this way, okay, so we can also write WPC transpose in a completely equivalent way, okay? So you can also write it as square root of alpha 1 up to square root of alpha 1 over 2. Alpha plus 1 over 2. רגע, in the middle, where? This? So,
The vertical line?
the vertical line.
No,
Here?
over here, that line?
Yeah, just, okay, you can just write it will be 0 actually, maybe. Okay? Okay, so I will explain what is written here, and also here we're putting UN dagger, UN. Okay, so
And is the dagger there also?
okay, so first, so this is the form of the optimal solution that you have seen in class, okay, before I'm discussing this. I just want to make sure that this is the form of WPC that you know. And now I'm
Well,
claiming
so
that
I don't, shouldn't those just be transposed? Why the dagger?
why dagger? Because we are dealing with the Fourier basis, which is in which you have complex numbers. Okay, so it should be.
This is the complex conjugate?
Yeah, this is the complex
Because
conjugate.
this is the matrix of the inverse Fourier transform?
Yes, yes.
Okay.
Okay. So instead of writing by this way, we can write WPC solution by this way. So this is M over N matrix, and this is N by N matrix. Okay. So you will see in the homework and why we can do it, but here we're just taking the M eigenvector and we adjust to each one of them the appropriate coefficients, okay? And in this form, we are writing all the N eigenvectors, okay? Not only the M eigenvectors, the M principal, we're writing all the N eigenvectors and adjust 0, okay, to all the vectors that we don't want to use. Okay, so these forms are equivalent. You will prove in the exercise why, so you will have time to think about why these two forms are equivalent.
It's a very technical question. The alpha n minus 1 over divided by 2 is like in the same row as the n.
Yeah, in this case because m is odd, so yeah. Okay. Little bit devilish, depends if order of them, but yeah.
Can I ask just a notation question?
Yeah.
The m plus 1 over 2,
Okay.
it's supposed to be like the minus? Why isn't it minus? Or
Because it's not the same as principal component, the next one.
no, not this one. The K is doing it.
Yeah, okay, so no, it's a good question. So forget for a moment this line, okay? This is just an equivalent way to write this solution without saying that we are talking about the retina of the Fourier or something like this. Now, here we say something that in addition to the general form of dimensionality reduction, when we are talking about the retina, okay, and we are asking what are the M principal components, so I said that in case of the retina, the principal components are will be the Fourier vector with the lowest frequency. Okay, so here that's saying that the Fourier vectors are the vector with the lowest frequencies, and here I just wrote alpha between 1 to m, which not mark here these numbers are not the frequency of the Fourier vector. Okay, this is just these are just numbers between 1 to n that mark the n principal components that we are taking. When you want to find which vectors you need to take, you need to use the fact that we're taking only the m lowest frequency, which will be the frequencies between minus m plus 1 over 2 to m plus 1. Okay, so it's not the same index that's here and here. Is it clear or not completely?
It's clear.
Okay.
And the minus is only on the M or on the
No, I think that it's over. How many? Yeah, we need to count the m lowest frequencies and think about it. I think that it's only over this one, but you need, like, it's just counting how many negative numbers and positive numbers you take in order to have m numbers together, okay? No, I think that it's only for the m. Only for? Okay, yeah, only for the m. Okay, so for now, all what we did was to write the optimal WPC solution in a different way, okay? So now I want to use this form of solution, and we call that we can do also something else to the optimal solution, right? So what can we, so we said in class that WPC is only one optimal solution, and we have many more optimal solutions, right? So what can we do to the WPC solution? Multiplied by what? By a unitary matrix. So can you guess which unitary matrix we will want to use in this case? Just guess. Okay, so you're right. So in this case, the unitary matrix that we will choose will be just, I'm calling it UM, okay? So the n-dimensional real matrix. So, okay, so this will be the solution that we will discuss, okay? And now I will show you that this form of solution, this matrix is very interesting, okay? And we'll discuss the properties of this specific solution. So the reason that we don't want to remain with this kind of solution is that, so imagine what are these Fourier vectors, these are sinus and cosinus, okay? So we don't expect that the receptive field in the retina will do oscillation and will take input from many different neurons in an oscillatory way. We expect that the input will be much more localized, okay? So when we apply the inverse Fourier transform, we can get something which are much more localized and get rid of this oscillation that we have here, okay? But now I want to discuss the mathematical properties of this form of solution because this is very interesting, okay? So this is the W that we're taking, and now, okay, so and just recall that here, maybe we'll do it this time. Okay, so the solution that we got is what we call a generalized circulant matrix. Okay, so W. Okay, and I will prove you that it has the following shape. Okay, so Wij is F of Pj minus I mod n. Okay? Okay, it simply means, so what is the form of this matrix, of this kind of matrix? So this is actually a matrix that each row is a rotation by okay, so what is, try to think yourself what is the shape of this kind of matrix. So for now I didn't prove you that this is the shape of the optimal matrix that we have got. Okay, we will soon show it. But for now believe me that this is the form of the matrix that we got, and try to think what is the form of this matrix. So it's very similar to the shift by Bauheimer test. Yoram just said it, but it's still most of the people that don't remember it. So for this matrix, each row is a circular rotation by p steps of the upper row, right? So this is exactly, so it's very similar to the regular circulant matrix that we had. So in the regular circulant matrix, each row just was a rotation by one step of the upper row, okay? So in this matrix, it's because this is not a square matrix, but so we have something which is shifted, so each row is shifted by a circulant rotation by p steps of the upper row, okay? So x1 and xp, okay? So this will be x plus p plus 1, okay, and so on. Okay, maybe I hope that I didn't write it in the wrong way. Yeah, maybe. Yeah, okay. So this is probably W transpose. Okay, so I think what I plot here is W transpose. Yeah. Okay, so
Does it have different properties from the existing matrix we talked about before?
okay, so first an important property that this is not a square matrix, okay? So this matrix does not have the regular form of eigenvectors and eigenvalues, okay? But still, we can do something which is similar to the diagonalization of this kind of matrix, and we'll get a very nice thing by doing it, okay? So now I want to prove. Okay, so now we'll prove that UM transpose W transpose UN and the QK component of this matrix is equal to square root of M F tilde K delta Q delta QK mod M. Okay, so imagine that now, wow, okay, I already erased it, sorry. Okay, so if we are multiplying this matrix from the left by the n-dimensional Fourier basis matrix, and from the right by the n-dimensional Fourier basis, we will get something that has this form, which is very similar to what we saw in the beginning. So this is F tilde K1 diagonalize W because it's not a square matrix, but if we will multiply W from one side by the inverse Fourier vectors of the m basis, and from the other side by the n dimensional Fourier vectors, we will get something which is similar to a diagonal matrix. Okay, so it's not completely diagonal, but we have, so everything is zero except these diagonal elements, which are equal to the Fourier coefficient of one of the rows of this matrix. Okay, so, and actually this form of the evaluation is what we just is what we just shown. Okay, is it clear? I think that this part is last year it was very confusing, so let me know if it's confusing. So, like mathematically, this is the mathematical equation that we want to prove. This is the way this matrix actually looks like. Okay? And now I will prove this mathematical equation. Okay?
Zero, diagonal, zero, then what
So,
did I just say? No. Then
Yeah.
zeros in the middle, and then
So, no, okay, so actually, this is M, and this is N.
You plug it
Okay.
into a computer and then you get an answer.
What?
You plug it into a computer and then you get an
Yeah, you
answer.
can't throw it in the middle of it.
Well,
It
there
just
are
like
columns
that.
that, yeah, that's like zeros
And
several columns.
no,
Zeros.
so this is a F tilde of the K equals M plus 1.
Okay.
Yeah, and then I did, sorry.
Okay.
Okay, yeah, I should make it more clear.
Three diagonals.
Okay, and okay, so we have many diagonals here because we have P, this kind, okay, of diagonal elements with all the H tildes. So it's even more confused because in the specific case of the racking out the dimensionality reduction, all the elements in the center are zero, okay? But in the more general case of W with this shape, there can be also elements here, okay? So in the general case of a generalized circular matrix with this form, if I'm not saying additional information about that, so there can be also elements here in the middle. In the specific matrix that we discussed regarding the dimensionality reduction, everything in the middle is zero, okay? Because that's what we get from the solution of dimensionality reduction, that we are taking only the M vectors, okay?
Instead of be as many as P diagonals, right?
Yeah.
Then did we say what P is?
That's the N over M. Okay, yeah, we said that we can write it again. Okay? When we assume that this is integer. Okay, so is it clear now? Like the shape of these matrices, and that's what is written on the board, at least. Okay, so now I want to prove this part, and then I want to discuss the properties of this transformation because it has very interesting interpretation. Okay. Okay, so we can do it here. Okay, so by definition, so the matrix UN, we say that this is the n-dimensional Fourier basis, so it's 1 over square root of n, just to remind you the definition, e to the 2 pi I kj over n, and we also have the UM matrix, which is the m-dimensional Fourier basis, so it's 1 over square root of m e to the 2 pi I j over m. Okay, so these are just the definition of these two matrices. Okay, this is thick. Okay. So now I will write explicitly the expression. So um dagger W transpose un. So the q k element of this matrix is sum over xy. So now xy will be the indexes in which we are doing the summation over. Okay, so sum over xy, 1 over square root of n, e minus 2 pi I qx over m f of px minus y mod n. Okay, multiply. So this is the matrix dagger. This is the matrix W transpose xy. Okay, and no, so I will just finish and then we'll see why. E to pi I ky over n. So we define the already. So I remind the definition of the so we said that W ij is f of p j minus I mod n, right? Okay, and now what I wrote you, I didn't want to use again the index I because we have I here. Okay, so instead we just wrote W. So this is W transpose xy. Okay, just look at the definition and it's fine. Okay, that's it. Okay, so now what I want to do here is so we will multiply this expression by exponents of 2 pi I kpx over n, and also divide by this expression. So what we get is 1 over square root of nm sum over xy in minus 2 pi I qx over m f px minus y mod n e2 minus 2 pi I k px minus y over n e2 pi I k px over n. Okay, so it's very technical part. Okay, this is just this expression we got it by just the definition of all the matrices that we wrote here. Okay, this is just the definition of the matrices. All what we did here was to multiply by this term and also to divide by this term here. Okay, that's it. Okay, fine. What are you trying to do? So we are trying to prove this
I think we believe you.
No, no, no.
Yeah,
Very
I
cool.
Okay, it's only one more line. Okay. Okay, so again the motivation. So I told you that the form of the matrix that is doing the applying the optimal and maximizing the reduction has a special form, okay? With all the diagonal elements and the zero of all that. And now I'm saying matrix that during the dimensionality reduction exactly has this form. Just show that it has this kind of form with the Fourier, with the multiplying by the Fourier method. Okay, so now I want to convince you that indeed this is the form of the optimal matrix that is during the dimensionality reduction. Okay, so we prove it, and then we'll discuss the properties.
No, this is the W.
This is the W.
We want to prove
So we want.
when you multiply from the right.
So when we multiply from the right and from the left, we get the diagonalized form. When we multiply from the right and from the left, what we are getting is the way this operator operates in the frequency domain, the Fourier domain. Okay? And this is so when we multiply from the right and from the left, we get this kind of thing, which is the way the matrix applies the dimensionality reduction in the Fourier basis. Okay?
This is the different dimensionality. Fourier.
So what appears in the dimensionality reduction is this matrix. Okay? It's this W after we also adding the unitary matrix UM from the left. Okay, so this is the matrix that we got in the dimensionality reduction, but I didn't prove that it has this shape. I only showed you that in the middle of this matrix we have this kind of diagonal form. Okay? So now I want to prove you that when we actually multiply from the right and from the left by the UM and UM, we get the generalized equivalent matrix, which will be the optimal transformation. Okay? Or not completely.
This is the W or this is the after the multiplication from the right?
So this is after the I don't already remember. Okay, so the W50 is when we also multiply from the left this by UM. This is the W50. Okay? What we're doing now is to take a general form of a generalized equivalent matrix, and we will prove that if we back multiply from the right by UM and from the left by UM dagger, we are backing to this form. So indeed, the W's after we add the unitary matrix UM has the shape of generalized equivalent matrix. Okay? No.
This is diagonal and there's this diagonal. I don't distinguish between the diagonal. There is a circle and matrix.
Okay, so this is
different.
no. Okay, maybe we'll skip the math at the end and we'll just explain the results because the math is very easy. But okay, the circle and matrix appears in different contexts. Okay, the circle and matrix in this context is the shape of the correlation matrix of the input. Okay, and here we got the optimal transformation that applies the input to the output. In this specific case, that the eigenvectors are the Fourier vectors, okay, has an interesting shape, and we call this interesting shape generalized equivalent matrix.
The shape is of the WPC transpose or just
The shape is of the interesting shape is of the matrix. Okay, so the interesting.
What is interesting? The result or just
The interesting shape is when we're taking is W, which is equal to the UM, okay, multiplied by the W50 transpose. Okay, this is the interesting shape. Okay, and I also multiply this by a square matrix, UM. Okay, and this matrix is is the generalized equivalent matrix with the shifted row, in which each row is at a p-step shifting of the upper row, okay? What we showed before. Okay?
We didn't have one of those originally?
What?
The circular? Didn't we start from a...
So yeah, it's confusing because the circulant matrix is of the input. Okay, now I'm not talking about the input. I'm talking about the transformation from the input to the next layer Y. And also this transformation, which does not completely relate to the statistics, to the covariance matrix that describes the statistic of the input. Also, this transformation has a shape of what we call generalized circulant matrix, in which each row is just a rotational shifting of the upper row.
In other words, the weight.
The weight. Now we're talking about the weight.
So the inputs are circulant, and also you're proving that the
Actually,
weights
it's
are
not.
also.
It's not. So it's not because the inputs are drawn from a matrix with a covariance matrix, which is a circulant matrix. Because of this, we can find an optimal solution. Okay, this is only one of the optimal solutions. We tell you that also this is an optimal solution, which is not generalized circulant matrix, looks like sinus and cosinus. But if we multiply the fifth solution from the left by we get the generalized circular matrix in which each row is the rotation of the upper row. Okay, so what is the meaning that each row is the rotation of the upper row? What does it tell us about the receptive field of the neurons, of the output neurons?
Same thing in a different.
Yeah, so it tells us that the output neurons actually do the same thing to the input, but they're taking the receptive field from a shifted number of neurons, or so doing the same thing but in a shifted way. So and it,
Fourier basis.
in the regular basis.
In the regular basis is
In the yeah. So in the regular basis, this is the generalized circulant matrix. Okay. This is in the regular basis because we already multiplied from the left by the Fourier. Okay.
UN is we have the output, no?
So okay.
And
So
you assume that it's
UN
circulant output. You have to assume that it's circulant output.
the output.
Yeah.
So yeah, we also get the statistic of the output. But UN is just the Fourier, the n-dimensional Fourier vector.
Of the output.
It's not coefficient. It's m Fourier vector in the dimensionality of the output.
No.
Okay.
Of the output.
Not of the output because it's not coefficient. It's that's m Fourier vector. I didn't say that I am applying the Fourier transform or something.
It's the inverse, no?
What?
It's not the inverse?
Sorry, the inverse. Yeah. Yeah, the emergent like this is the inverse.
So the WPC is in Fourier basis?
So the WPC is applying is adjusting to each Fourier. It's not exactly in the Fourier basis. So what is written in the middle? Okay, so now so we don't have time to do the formal proof of the equation that I wanted to do. It's very short. It will be in the notes. It's only 2 lines, additional to what I already wrote you. So I want to now discuss the meaning of this transformation. Okay, what actually this transformation does. Okay, so assuming that you believe me that this is true, okay, it's not hard to see it yourself. So now I want to discuss the properties of this matrix. Okay, so W is a matrix that operates in the regular basis. Okay, in the space, in the neural space in our case. But when we multiply this matrix from the left, what is this? What is UN according to our notation? What? The inverse Fourier transform. No, we said that UN dagger. When we're doing the Fourier transform, we are multiplying by the conjugate of the vector. Okay, so UN is the inverse Fourier transform that returns us from the Fourier basis to the regular basis. Okay, and UM is the Fourier transform that takes us back to the Fourier domain. Okay, so actually the meaning of this transformation is what the dimensionality in the frequency domain. Okay? So now think that you have, instead of having the activity of the neuron, we have the Fourier coefficient of the activation of this neuron. Okay? So this matrix will tell us what happens in the frequency domain. Okay? So in the frequency, so actually this is what happens in the frequency domain. Okay? So if we're working in the Fourier domain, what is the vector in the Fourier domain? What is an n-dimensional vector in the Fourier domain? What is the meaning of an n-dimensional vector in the Fourier domain?
Frequency.
So this is the vector of all the coefficients, right? All the n Fourier coefficients of the functions in the space domain. So this transformation tells what happens to the Fourier coefficients of the input. Okay, so we're starting with an n-dimensional vector that has n different Fourier coefficients, right? Because this is n-dimensional. And the output is something that has only m-dimensional, which is only m-dimensional, so it has only m different Fourier coefficients, right? So this matrix tells me what happens in the frequency domain, how the Fourier coefficients of the output, okay, are determined by the Fourier coefficients of the input. Okay, so actually we can say that what's happening is so all this. So what are what is the first row of this matrix? What is the first row?
F J equals 1, F J
Yeah.
equals M plus 1.
Okay, but what first row does? What it tells me? Tell me how the first Fourier coefficient of the output will depend on all the n Fourier coefficients of the input. Right? This is what the first row does. Okay? Is it clear? Yeah, I will repeat it because it's important. So when you're looking at the first row, so the first row tells us how the first component of the Fourier vector in the n-dimensional output will depend on all the other n Fourier components of the input. Okay? So it tells me that because we have almost everything is 0, right? So the first Fourier vectors of the output consist of the first Fourier vector of the input, okay? The k equals to m plus 1 Fourier vectors of the input, right? And until the k plus p minus 1 Fourier, okay? So we need to finish, so we'll do it quickly. Okay, so okay, so I wrote it explicitly, but so the first component of the output, the first component of the output consists of the first component, the m plus 1, the 2m plus 1, and so on component of the input. Okay, this is what you can see from here. So why this property is interesting and something that we maybe could have expected? Because recall now that when we talk about the Fourier basis, we said that we have the property of the circularity, right? So actually, in the Fourier basis, in the n-dimensional Fourier basis, all these vectors look exactly the same. Okay, do you remember it? That we said that we can always add an integer number of the dimensionality of the basis. Okay, we saw it explicitly for the 0 and the n frequency. So if we add an integer number of n, then all these vectors actually look the same in the dimension of the output. Okay, so the way we do the dimensionality reduction in this way actually makes sense. Okay, so in the n-dimensional vectors, these vectors are different. Okay, if we have n points of sampling, all these vectors are different. But when we have only m points of sampling, all these Fourier vectors look exactly the same. Okay, and this is the way that this matrix applies to dimensionality reduction. It adjusts to the output vectors that in the input don't look the same, but in the output, all the vectors that are adjusted to the same component look the same because of the circularity of the Fourier basis. Okay, I also wrote it in the notes.
Like remove redundancy?
Yeah, like this because
Like everything is the same.
because in this basis, in the output basis, all these Fourier vectors look the same. Not in the input, but in the output. Okay, so this is the interpretation of this transformation in the frequency domain. And what we actually, in the general form of the general circulant matrix, in the case of the retina, we're finishing now, okay? In the case of the retina, it's even more simple because we take only one component to the output. All of this is going to be 0. Okay, in the case of the retina. In the case of the retina, we apply the dimensionality no, because it was 0, this part was 0, and this part was 0. It had half diagonal here and half diagonal here. Okay, so in general, when we want to apply dimensionality reduction by a generalized circulant matrix, so a generalized circulant matrix adjusting frequencies that look the same in the output domain but not in the input domain. In the case of the retina, it's even more simple because each frequency, because we just adjust 0 to all the high frequencies and taking only the lowest, so we have all these coefficients are 0. But in the general form, it will not be 0. Okay, I think that this is maybe the hardest PA session that could be. Okay, so feel free to ask me questions about that. It will be in the notes. Okay, and let me know if you feel, I think that it's a little bit difficult, so let me know if you don't understand and you need help. Okay? Bye bye.
זה להפחית כאילו להפחית מי אלה? אנחנו
לגמרי נראה את הנפש של הספנים,
הפריטה הזאת, את W?
כן, כל כך כאילו את הראשון, השני, עד
לא, אנחנו רוצים להפחית זה המשקולות.
זה המשקולות, אנחנו כאילו מזרים את ה-I,